Okay, hello everyone again. Welcome to part 2 of this introduction to COCO and ChemSep. And in part 1, I talked about sort of the general features of COCO and ChemSep, and I compared COCO and ChemSep to Aspen. And in part 2, this is where we're really going to get into the details of how to use COCO, how to use ChemSep. And so if you follow along in part 1, you will have COCO installed on your computer. So your Windows desktop should look something like what you're seeing right now. You should have an icon for COCO. And then for future work, it's nice to have a shortcut to the software Configure Corn on your desktop, and also Configure T on your desktop. But today we're just going to use coffee. And I have a little example problem here. And I'm going to make this example problem, or it actually is available on my course website. So if you go to my personal website at UMBC, so the website for Doug Fry at UMBC, and you navigate from there to my course website, you'll see this example problem. And what we're going to do here is we're going to separate a hydrocarbon mixture. So it's going to be a mixture of benzene, toluene, and 3 xylene isomers. Distillation will be the method that we use. And in fact, there will be 3 distillation columns. So the first column shown here is going to be the column that's going to remove benzene from this mixture of benzene, toluene, and xylene, so BTX. First column will remove benzene. Second column is going to remove toluene in the overhead. Normally, we would take that toluene and it would go into a transalkylation unit, and it would convert toluene to benzene and other xylene isomers, because the xylene isomers are the most valuable part of this hydrocarbon mixture. And I don't have that transalkylation unit in this problem. And then the third column is the Xylene Splitter. So it separates and recovers orthoxylene from the bottom of the column. That's the heaviest hydrocarbon in the starting hydrocarbon mixture. And then it has an overhead product that still contains a fair amount of toluene and orthoxylene in it. So that is directed to a separate unit, which I call the paraxylene separation unit, or paraxylene unit for isolation. And I represent that by a simple Excel spreadsheet. So I'm going to take the opportunity to show you how to incorporate an Excel spreadsheet into this problem. And we're going to recycle the toluene and the orthoxylene back to the toluene column. And that's the basis of the problem that we're going to try to solve. And so I have some specifications here, and these specifications are going to come up again. So the benzene column, we're going to have 98% recovery of benzene at 98% purity. And then as a very rough starting guess for the column, we're going to have 36 plates total, and the feed will be at plate 18. And the second column is the toluene column that recovers toluene at the top of the column. 85% recovery of toluene in that top product, the distillate product, at 95% purity. And as a very rough approximation, we're actually going to fine-tune the design of the column as we go through the problem. But a column with 72 plates and with the feed at plate 36, that's kind of a rough starting guess. And then the final column is the Xylene Splitter. And the idea is we're going to recover orthoxylene in the bottom product of that column at 95% purity and a recovery of 90%. And this column, rough approximation, has a total of 136 plates, and so it's among the tallest columns built worldwide for distillation. And approximately the feeds at plate 68. Again, we're going to refine all these numbers later, but I have this kind of starting guess so we can get a simulation that works, and then we can refine it later. Okay, so that's the basic column setup. And a couple of other details here. Again, you can read this problem in more detail on my course website. And one more detail I'll mention here is that the stage efficiency is assumed to be 0.8. So I assume we don't reach equilibrium on each plate, which is realistic, but we get 80% of the way to equilibrium. So a stage efficiency of 0.8. Okay, that's the problem we're going to solve. And we're going to solve it using COCO. And so the first thing we're going to do after installing COCO is to open up Coffee. So Coffee is the Cape Open flow sheet environment. And when you open it up, you should have a blank flow sheet. That's as shown here. And I actually have the solved problem to take a look at here. So when we're done, or when you're done, you're going to have something that looks like this. Again, 3 distillation columns, the benzene column, the toluene column, and then the xylene splitter. And we're going to recycle toluene and orthoxylene back to the toluene column. And that's going to be our process. But to start, we have a blank flow sheet. So how do we get started? So the first thing we want to do is to define a thermodynamic model for the system. And it's going to be a thermodynamic model that applies to the whole flow sheet. So the first thing we have to do is click on the settings node. In your case, you're only going to have one main node here. I've got 2 main nodes. The flow sheet I'm working on and the solved flow sheet, but you'll actually have only one. And click on the settings, and you'll get a window that looks like this. We're going to add a new thermodynamic model, so you click on Add. And we have a couple options. I'm going to use the ChemSep Thermodynamic Property Package Manager. And so select that property manager and hit Select. And we're going to have a new package. So click New here. It's going to be a new package. And after a couple seconds, you'll see the ChemSep part, the thermodynamics part of the ChemSep software. And so the first thing we're going to do is define the components. And so the components are going to be benzene, toluene, and the 3 isomers of xylene. That's the ortho, meta, and para xylene isomers. So we have to find those. So you have to transfer them from the list of possible components on the left-hand side to the window on the right-hand side. And I'm going to use the find window. And so if I type BENZ, that's a unique identifier for benzene. And I can click the Add button, and I can put benzene in the right window. And now the same thing for toluene. So TOLUE, and that's a unique identifier for toluene. So I transfer that. So now I've got benzene and toluene. You can see benzene and toluene are the names of the components here. And then I've got the xylene. So I start typing X, Y, L. And now you can see I've got the meta, ortho, and paraxylene. So I'll click on first metaxylene and add it. Then I have to repeat that. So X, Y, L again. Orthoxylene, add it. And X, Y, L again. And paraxylene. And now add it. So at this stage, I've got the 5 components of interest in the system, but now I have to define the thermodynamic model. So I click on Properties, and under K value, I'm going to select gamma phi. And gamma phi means I'm going to use a equation of state for the vapor and a completely unrelated model for the liquid. So gamma phi, the gamma comes from the activity coefficient for the liquid, and the phi is the fugacity coefficient in the vapor. So 2 essentially independent models. I have other choices, but I like to use gamma phi. My equation of state, I'm going to select the predictive Soave-Redlich-Kwong equation of state. And it auto-selected UNIFAC for the activity coefficient because that's a logical combination with my equation of state. The predictive Soave-Redlich-Kwong equation of state uses the UNIFAC model for the binary interaction parameter, so it makes sense to use the same model for the activity coefficients in the liquid phase. You wouldn't have to do that. You've got other options for the liquid phase, but that combination works pretty well. And the reason I like to use it is because when I add components to the physical property database, I know exactly what physical properties I need to use the predictive Soave-Redlich-Kwong equation of state and the UNIFAC model. And there's not much that has to be done there. I just need the critical constants, the eccentric factor, and I need the heat capacity as a function of temperature, the Antoine constants, and then I need the functional groups, in other words, the structures of the molecules, in order to use the group contribution method for the activity coefficients or the binary interaction parameters. So again, predictive Soave-Redlich-Kwong for the equation of state for the vapor and activity coefficient UNIFAC. That's a pretty good choice simply because it's very easy to add components if you use that choice. Vapor pressure Antoine equation for the vapor pressure. And for the enthalpy, I'm going to assume ideal liquid mixture, and that's a simple enthalpy calculation. Works pretty well. And you can see I've got green check marks everywhere, so I'm basically done now with defining my thermodynamic model. And this model is going to apply to every unit in my flow sheet. So what I do now is I save it. Okay, so hit save. And then I can exit. So here I exit, and it's going to ask me to confirm a couple things in a second. I think it's going to get there. Just be patient here. Okay, one thing to note, I'm going to try it here. If you see the ChemSep icon down here, it means it wants you to hit that. So I think that's what happened. So if you ever see the ChemSep icon down here, the reason why it's not responding up here is because it wants you to hit that. So I'm going to hit that, and it gives me this error code. It's good to know what that is because that's an error code that you can actually ignore. So just say OK, and it gives me a second one I can also ignore. And now you can see that icon's gone. And now it asks me if I want to assign that package to basically every stream in the process flow diagram, and I do want to do that. So I'm going to hit yes when it says assign property package to the default stream type. And now I basically have my thermodynamic model defined. I should check it by clicking on the Compound tab, and I'm going to see the 5 components of interest here. And the second way to check it is if you hit or click on the stream types, which I just did, and you can see all 5 components are going to be in the default stream type. Essentially, every stream is going to have all 5 of these components. I find that the simplest way to do it, to assume all 5 components or all the components are present in every stream in your process flow diagram. You wouldn't have to do that, but it gets confusing if you pick and choose. Some components are present in some streams and others are present in others. So simply assume all the components are present in every stream, and if a component's really not there, it will just have a mole fraction of 0. That's usually the simplest way to do it. Okay, so once you get to this stage, you're all set to go as far as your physical property thermodynamic model. So you can hit the red X here and get rid of this window, which I just did. And now you're ready to insert streams and processes. So let's start with our first stream here. This is going to be our feed stream to the process. It's the benzene-toluene-xylene stream. And what I'm going to do is, first of all, left-click on this Insert Stream icon. So simply left-click and let go. And then I left-click again and let go, and then move the mouse, and then left-click one more time and let go, and now I've got a stream. But you can see the stream is sort of this green color, which means it hasn't been specified yet. So we need to tell COCO what exactly is in that stream, and I'm going to do that now. So I right-click on the stream, and I go to Edit View Streams. So again, right-click on the stream, and then left-click on this Edit View Streams. And now I can specify what that stream actually is. So the pressure, it's in pascals, and I'm going to say it is at 1 atmosphere, so it's 101,325 pascals. Temperature, I'm going to say, is just basically room temperature, so 298 K. And then the feed composition was specified in the problem statement. I'm going to say, or the specification was 0.33 mole fraction benzene, 0.34 mole fraction toluene, 0.11 mole fraction for all the xylene. So the mole fractions will add up to 1. And then the flow basis is just going to be 1 mole per second. So change to 1 mole per second. And now we've got the stream totally defined. Okay, and if you want to look at the properties, you can click on some of these tabs, and it's calculated all the thermodynamic properties like the enthalpy. And you want to check the phase condition. It's all liquid because at that temperature it's basically subcooled liquid. And if I want to look at the compound flows, it's pretty obvious. You take the total flow rate multiplied by the mole fraction, you get the flows of each compound. So that's defining my feed, and I'm going to then click the black X. Make sure you don't click the red X above it because that's going to close all of COCO, but you just want to close this dialog box. And now, if you look carefully, you can see that that stream is now black, meaning it's been properly specified. Okay, so now we're going to start with the column. And one thing I want to show you here is in this example problem, we are going to split this mixture. So the feed mixture is this benzene, toluene, and para, meta, and orthoxylene. And I've arranged the components in order of their vapor pressures here. Relative volatilities, in other words. And the first column, we're going to split the mixture between benzene and toluene. So in the terminology that's used here, benzene is going to be our light key component, toluene will be the heavy key component, and these xylenes will be the heavy non-key component. So the split is going to be between benzene and toluene in that first column, and we're going to get that 98% benzene at 98% recovery in the first column. For the second column, the split will be between toluene and the xylenes because the benzene won't be there anymore. And the split will be between toluene and the xylenes. So the toluene is going to be the light key, and then the paraxylene will be the heavy key, and the other xylenes will be the non-key components. And then finally in the last column, because toluene will not be there, and we're taking the product out the bottom, the split is going to be here, and we'll be taking orthoxylene out the bottom of the column as the bottom product primarily, and then the other components will be the heavy keys and the heavy non-keys. Or excuse me, the light key and the light non-keys. Orthoxylene will be the heavy key in that third column. Okay, so back to our COCO flow sheet. Next thing we're going to do is set up that first column. So I go up to the icon, which has the unit operations, and I click on it, and we're going to select the separations node, and we're going to select ChemSep, because ChemSep has all of the standard unit operations, distillation, absorption, etc. So we're going to select that. So select the ChemSep subnode and select it, and we're going to put it near the feed stream by left clicking so it gets anchored, and we have the unit operation located. But now we're going to have to set it up, because you might notice if we click on our feed stream and then grab the exit end of that feed stream, we cannot connect it to our unit operation yet because the unit operation hasn't been defined. So again, you can left click on the stream and then left click and hold it there and try to drag it into the icon for the distillation column. You can't connect it because the COCO software says, hey, you've got to at least open it up and take a look at it before you're allowed to connect anything. So that's what we're going to do. We're going to right-click on the ChemSep icon and go to Show Graphical User Interface. So click on Show Graphical User Interface. And now it's going to show you kind of an intermediate dialog box, and you can change some of this. We're going to change it in the graphical interface itself, but the thing that's kind of most interesting is the very last option here. I got two options. I can use the Cape Open thermodynamic model that I just defined, or ChemSep. If I select the ChemSep option, and I actually don't want to do that in this problem, but if I do, I can actually redefine a new thermodynamic model that applies only to that process. And sometimes that's useful to do. But I'm not going to do that, so don't do that. Select Cape Open here, and that's going to use, it's going to force this unit operation to use the thermodynamic model that we defined earlier. So with those selections, you can select OK. And again, it may take a little while to open up because it's opening up the graphical unit interface for ChemSep. And there we see the graphical unit interface for ChemSep. And you can see all the nodes in the node tree. Most of them are already green. In fact, they're all green. So they all have default values which we have to check. So we might check first the components. And you can see it knows that it's got those 5 components present. Okay, so components, those are the components present. That's all correct. Operation. Let's check operation. So it's assuming a simple distillation column. That's okay. The condenser is a total condenser. I'll just leave it as a total condenser. Reboiler is the partial reboiler. But remember, we had an approximate design of the column. As I remember, it was 36 total plates. So you want to change the number of stages to 36. And it's asking if it will allow it to automatically change the feed plate location. So it will estimate, and it estimated correctly that you wanted the feed stage at 18. It just puts it in the middle. Obviously, you can change that if you want to. And you can do all sorts of things. You could have 2 feeds present if you wanted to. I only have 1 feed here, so you just put 2 plate numbers separated by a comma. Notice the numbering scheme for the plates. The condenser at the top is plate number 1, and the plates are numbered going downward, and the reboiler at the bottom is plate number 36 in this case. So that is my equilibrium column, properly defined. And the feeds, let me click on the feeds. The feeds, we don't have to do anything with it now, because when we finally connect that feed stream with the column, it's going to put all these numbers in there properly. In fact, we're not able to put numbers in for the mole fractions or flow rate of the feed. So we don't have to do anything with the feed. But the column specification, well, okay, so we do have efficiencies. So let's click on the node for the efficiencies. And remember, the problem says that the stage efficiency really is 0.8 for the stage efficiency. And so I'm going to put 0.8 in there. And to make sure that it's actually entered, I have to hit return. If you just put a number there, it's not really entered. So hit return, and now it's really entered. So 0.8 for the stage efficiencies. Column specifications. So it's got default column specifications. The reflux ratio is 2 fraction of combined feeds in the bottom product, I think. Yeah, the fraction of combined feeds that exits the bottom is 0.5. We don't want that. Top specification. We actually have 2 specifications for the top. We've got for benzene 98% purity and 98% recovery. So we have to change it. So top specification, let's put in the purity. So mole fraction of a component is what we want to do. And it assumed that we wanted to specify something for benzene. We could change that, but it says benzene. And we change the number to 0.98. And again, it's not really entered unless you hit return. So let me hit return. Now it's entered. That's the top part. And one of the things about ChemSep is it wants you to specify something about the top and something about the bottom. Now, the problem statement had really 2 things about the top. So it had the mole fraction of 0.98, and then the recovery of benzene at the top was also 0.98. So we have to convert one of those to something about the bottom. And sometimes that's easy to do. Sometimes you have to do an offline material balance. But in this case, it's very easy because if we're recovering 98% of the benzene in the top product, and recovery means of the material, of the benzene entering the feed, what fraction is exiting in the top product, the distillate product? The answer is 98%. So obviously, 2% of the benzene is exiting out the bottom. So for my bottom specification, I can select component recovery. So component recovery, and again, it's benzene, but it's 2%. So change the number to 0.02. Remember to hit return to make sure it's entered. And now I've got the proper specification. I've got 98% purity of benzene at the top, and 2% recovery of benzene out the bottom, which means there's 98% recovery of benzene in the top product. And those are the specifications for our problem of interest. So the problem is totally specified now, except for the feeds, and the feeds will be entered after I connect the feed stream to the column. So I'm actually done. So I go up to the feed menu and first, or file menu, and first I save. Okay, so save it, and then exit. And it wants to know if it can update the coffee icon, and so sure, go ahead. And so it's updated now, the coffee icon. And now I can actually connect the feed stream to the column. So I left click on the feed stream, and you can see there's a big black dot on the arrowhead. And so I can grab that arrowhead, and now it allows me to connect it to the column. And after I connect it to the column, we'll take a look at it in a second, the feeds will be in that feed node, okay? But now I've got the two product streams to put on here, so I just left click on the stream node, or the stream icon at the top, and then I left click at the top of this icon, and then move the mouse over and left click again. And it wants me to confirm that that's the top product, and yes, it is the top product. I think you could actually locate that stream anywhere, but I like to connect it kind of at a logical location. And then I've got to do it again for the bottom product. So I go up to my stream icon here, my insert stream icon, left click on it, and then bring the mouse. Then I left click again and let go, and then left click again, and now I've got my product stream. And notice that the icon turned black. The icon for the distillation column turned black. If you hover the mouse over it, it says everything's okay. Maybe we'll take a quick look at it to make sure the feed has been properly entered. So right-click on the icon, show graphical user interface. Might take a couple seconds to open up. Everything should be the same. The only thing that's new is let's click on the feed node. And now you can see the mole fractions are properly entered. Okay, the mole fractions are properly entered. The units are in kilomoles per second. That's okay. So they're going to be 1,000 times smaller than how I entered them in the actual feed stream. I can actually change the units if I want to. I probably should have done that. If you go to the units node, you can change those units, but I'll just keep them as they are. So that's all okay. So I'm going to exit out of here, and I probably wouldn't have to save it, but I'm going to save it again, and then exit. And it's probably, no, it didn't ask me to confirm anything. Okay, we're ready to run this thing. There's several ways to run it. You can right-click on it, and you can calculate this unit only. Okay, so I think I'll actually do that. So calculate this unit only. And when it's gold or yellow, it means it's calculating it. And it actually finished it. So we know that it ran okay. But another way to run it is to hit the Solve button at the top. You can also do it from the flowsheet menu and hit Solve. But I'm going to click on Solve here. It's already solved, so this won't take much time. But I'm hoping it's going to show me an error message. Yes, it does. Remember this error message because it's harmless. In fact, you should be happy when you see that because it means everything is working. So this particular error message is harmless. It's going to happen a fair amount. You just say OK, and it's going to follow up with a second message that says it can't find something. That's okay also. Remember those error messages and information boxes because those will happen quite a bit. You just can ignore them. And notice everything is in green. And that means it's been solved you can hover the mouse over the product stream and you can see the mole fractions and the flow rate. Hover the stream over the top product and you can see the benzene mole fraction is 0.98. That all looks good. Now let's open up the graphical user interface one more time, because I'd like to take a look at some results here. So for example, under graphs, take a look at liquid phase composition. And here are the composition profiles of all the components inside the column. The top is the top of the column, so the condenser is at the top, the reboiler is at the bottom, and you can see the red is benzene, so we've got 98% benzene that comes out the top. We also have a little bit of toluene, it's about 2% toluene. The xylenes, being the heavy keys, really don't travel up the column much at all, so the 3 xylenes actually die out above the feed plate. The mole fractions die out pretty quickly. The xylenes have this region below the feed plate where they have fairly constant mole fraction, and then the mole fractions change somewhat as you get down to the reboiler. The toluene is the heavy key in this problem, has kind of complicated behavior, but it's kind of interesting to see the mole fraction profiles. So make this graph go away. You've got all kinds of graphs you can make. For example, temperature profile in the column. This is what the temperature profile looks like in the column. And by the way, you can export all these numbers into Excel, and you can make your own graphs. You can make tables instead of a graph. And again, export everything into Excel. But the thing I want to look at is this new node that didn't used to be there called FUG. Fensky, Underwood, and Gilliland, FUG. That's the shortcut method which we're going to use. If you're familiar with the Fensky, Underwood method, it's a shortcut method to give you an approximate optimal design. And so click on that node, and it's kind of a self-contained node in ChemSep. It auto-identified the light key and the heavy key. So the light key is benzene, the heavy key is toluene. The only thing you can adjust are the recoveries of the light key and heavy key. So we're going to have to play around with these to get the specification we want. So the first one is the recovery of benzene in the distillate. So D stands for distillate. We do know what that should be. It should be 0.98. So change that to 0.98. Now, the recovery of toluene in the bottom product, we actually don't know what that is. What we know is we want 98% purity of benzene in the top product. So we actually have to play around with this second number to get the purity we want, but I've done this ahead of time. And I know, because we have a kind of a symmetrical mixture, if I put 0.98 for recovery of benzene in the bottom product, I get my 98% purity of benzene in the top product. So I think I said that wrong. 98% recovery of toluene in the bottom product. It changed the mole fraction of the light key in the distillate, so XLD, mole fraction of the light key in the distillate, got changed to very close to 0.98. So that basically is our specification. I've got the selection of the reflux ratio, and it's in terms of the design reflux ratio over the minimum reflux ratio. And you might know approximately the optimal ratio there is about 1.2 or 1.25. And again, I could change that. If you change any of the 3 numbers in those 3 boxes, the bottom part of this spreadsheet will just automatically recalculate, and it does not affect the rest of the ChemSep file. So I'm going to leave that as 1.2. And now it's calculated using the Fenske-Underwood method, approximately the optimal design. And so we can just see what it is. It's 21 stages with feed at stage 10, but it does assume that the stage efficiencies are 1. So my stage efficiencies are 0.8, so I should really add 20% to those to get an approximate optimal design. So that means around 25 stages with my feed on stage 13. That should be approximately an optimal design. So I'm going to go to the operation now and change it to this approximate optimal design. And I already kind of forgot what I said, but I think it was 25 stages and the feed on stage 13. So that's approximately an optimal design. Now, of course, to do better, I should do case studies, rigorous simulations around that approximate optimal design point and do case studies. And I can actually do that if I go to ChemSep and look at the, I guess I don't have the parameter sweep here. I guess I actually cannot do that. I can actually do that in Coffee, but you may want to play around with the feed plate and the number of plates to check that you've got the optimal feed plate, not using the Fenske-Underwood method, but using rigorous simulations. I'm just going to assume approximately 25 stages and total 13 stages. And I could actually recalculate this right now. No, actually I cannot. I've got to save it and then exit. And now you can see my icon is in black. It means it's properly specified but not solved. So I'm going to solve it again. So I go up to the solve node and say solve it. And it's probably going to give me that error that I can ignore. It does. Again, remember what that error looks like. And it's a rare case where you should be happy if you see that error, because it actually means things are working. So just say OK, and then once, I should probably fix this. I cannot find a certain file, but it doesn't matter. And it could even show me that several times if it's iterating. But now I've actually solved the first column. So I'm going to end part 2 of this tutorial right here. We've solved the first column. And part 3, we'll solve the second column, and then I'll show you how to incorporate an Excel spreadsheet into a Coffee flow sheet. So this will be the end of part 2. So I'm actually going to exit out of here, stop sharing this, and I am going to end the meeting here, which I do with this button, stop the recording right here.